Okay, so the question is, how do you choose your switching frequency, right? That was a question. How do you size your filter?
I was wondering about frequency
Mhm.
and how frequency relates to the low-pass filters, and we went into the idea that the limitations on frequency comes from the switch.
Okay, so switch. When we were drawing this device turning on and turning off, I was drawing this, rising in no time, right? This is rising from 0 volts to 9 volts, for example. I was drawing this rising in no time, but there's no such thing as no time, right? So actually, it will depend on the switch that you choose. So this is one type of switch. So let's see. This is a MOSFET. It just happens to be a MOSFET, and let's see where is the something related to the time. So here, this is nanoseconds, right? So there's the devices will have rise times, and they will have fall times. So where's the fall time? So this is the fall time. So they have rise times and fall times and some delay times. So delay is, internally the device. Remember MOSFETs, you have to create the channel. After a certain threshold voltage between the drain to source, the channel forms. After the channel, so first you have the depletion layer form, then the channel forms, then you can have conduction, right? This takes time. That's delay time, right? But you've already put the voltage between drain to source, so between the gate to source in a MOSFET. You've already put the gate to source voltage, but you're waiting for this time. This delay time is where, okay, the device is getting ready to conduct, or the device is getting ready to stop conducting, right? And then this all requires time, and current is what? The movement of charge. There we have a channel in the MOSFET where, the electrons or the holes, depending on it's a p-type channel or an n-type channel, the electrons or the holes were moving through the channel from drain to source or source to drain, and that's current conduction, right? All of this takes time. So and that is what's accounted for here in rise times and fall times. So this is a turn off delay time. So there's a turn on delay time, and then the rise time. So you ask the device to be on, it prepares itself to be on, and then the current starts rising. And then you ask the device to be off, it prepares itself to be off, and then the current starts falling, right? So it's about 110 nanoseconds, 110, 115, 110, 110, or 150, 115, about 100 nanoseconds for this device, right? So it takes 100 nanoseconds for it to rise, 100 nanoseconds for it to fall. So you would like this rise and fall. You don't care about the rise and fall. You don't want to account for this rise and fall time. You want this rise and fall time to be a lot smaller than your period. Your switching period here is what defines the amount of time the device is on, which is what defines, the integration 0 to t over 3, 0 to t over 4. Remember we were integrating x of t, which was the voltage, for example, from 0 to t over 3. If this was t over 3, we were integrating from 0 to t over 3, and then we don't care about this from 0 anyway, right? So then we were finding that this was the average value, 1 over the period, integration of the waveform over the period, and that was giving us the average value of the waveform that we have. So did I consider at all the rise times and fall times? No. So how about if you make your switching period, t, which is, by the way, inversely proportional to the switching frequency, right? Time and frequency are inversely proportional, right? So time is equal to 1 over frequency, frequency equal to 1 over time, right? So your switching frequency or your switching time period, let's say you shrink that. If you shrink that and use the same device, what will happen? So I shrink my TS, my switching period, I make it here. So I still want to, this is my T over 3. This is my T over 3. If I do this, if I'm able to have the device on from 0 to T over 3, and then 0 from T over 3 to T, then I'm getting the same average value. Do you agree? I will get the same average value because it's, the same waveform. It will be fixed value here. But now I'm using the same device, And the same device, if I shrink the time a lot, now this rise time and fall time will become a significant amount from that switching period. So now I have a waveform that looks more like this. Does not look like this, right? I mean, these are the same peak values. I'm talking about this area, these areas here, right? It's time to rise, time to fall. So what does this mean? It means that my average value in this case has decreased. Really, it's not the average value that I was thinking I was getting in, right? So this is what's going to limit your switching frequency. This is one thing that will limit your switching frequency. Typically, you'd like to switch as fast as possible, right? But then you are limited by the switches rise times and fall times. Not only that, the switches rise times and fall times also, remember we said, okay, it takes time for the current to rise. When the current rises across a switch, what happens? When the current rises, meaning I have now current, this ID current is rising from 0 to value ID. What is happening to the voltage across the device? It becomes a short. It's like a short circuit, right? So the voltage is falling. So the voltage is falling and the current is rising. And both of them require time, right? So now I have current rising and I have voltage falling during this period. So what do I have during this time here when the switch is moving from non-conducting? This is the red is the current and the green is the voltage. So this was not conducting and then now conducting. Not conducting and then it's going to go back to conduct. So what do I have here? Here I have, voltage V and current approximately equal to 0. So what is my power loss? Approximately equal to 0. Approximately, right? There's no such thing as 0. There will always be a current. When the device is off and you have voltage across it, there will be a leakage current, right? Like in capacitors, you studied the dielectric material. You have a voltage, there will be a leakage current. Very small amount, but there is something. But for us in power electronics, we will approximate it to 0 for now. So it's approximately 0 here. But how about here? Here I have voltage and I have current, right? So if you look at your power losses in the device, there will be a huge amount of power loss, a big spike in power loss when you're switching, right? So this will also be tied to the device that you choose. So if I look at this device, power dissipation. This power dissipation, this device allows peak power dissipation of about 200 watts. If you dissipate more than that, what happens? You burn it. So 200 watts. If you have 110 amps and 55 volts, that's much more than, if you just multiply them by each other, it's much more than 200. Right? So what do you have to do if you're going to be running this device at full voltage and full current? Definitely you have to have a cooling system. You will definitely have to have a cooling system, or you have to make sure that you utilize a certain topology or switching algorithm, that reduces the current before, or reduce the current before the voltage rises, or vice versa, so that you reduce the power loss.
So does that mean if we increase the frequency of the switching, we have more
losses?
dissipation?
Of course, you have more switching loss. There are two types of losses. Okay, there are in this when the device is on, we call the. Remember, we said when the device this is the device on, right? We said that there's always going to be, here the voltage theoretically went down to 0. Is there such thing as 0? No, because this is a MOSFET, right? We are operating the MOSFET in cutoff. This is I, this is V. We're operating the MOSFET in cutoff and triode region, cutoff and triode region, right? Ideally, yes, we're up here, but in reality, we are actually following, this is the MOSFET's curve, right? We're actually following this, we're operating along this line. We're trying to operate along this line only. What's happening along this line? When I have current through the device, this is current I, so I have current I here through this device. I have a certain voltage drop across the device. This is the voltage drop across the channel, right? The channel in the MOSFET, it's a channel, it's a conducting material. This conducting material has equivalent resistance. this equivalent resistance, if you look at this, the MOSFET's voltage and current curves, right? This is a linear relationship in this portion here. If we're operating in triode region, in this part of the curve of the MOSFET, then there's a linear relationship between current and voltage across the device. So in 325, we took the slope, the inverse of the slope of that, and we called it a resistance. We call it the channel resistance, right? So and that's what we have. We have a. If we look at the data sheet now, they will give you a channel resistance, RDS on. So this is an equivalent channel resistance. So you will have a channel resistance, and you will have a certain amount of current flowing through. You can calculate how much power loss. This device allows you to dissipate in this package. Okay. I will show you other packages, but this is a this is called a TO220 package. This is called this shape is called TO220 package. There's TO247. There's other so many other types of packages, and each type of package, the silicon inside it is the same. So it can be the same device physically. Silicon inside can be the same, but the package can be a package with a metal on the back. If you have metal on the back versus plastic on the back, metal is a better conductor of heat. Right, so you can dissipate heat better. So if you put a heat sink, you have better luck at dissipating the heat out of the device. So you'll be able to maintain the device temperature within a limit. So device, they tell you a certain power dissipation, and they also tell you operating junction temperature. So operating junction temperature is between for this device minus 55 to 175 degrees Celsius. So this is the maximum temperature that you can operate the device at. At 175, they expect you to put zero current through the device. At minus 55, you can put full current, and all of that is detailed in all these different curves and data sheets. So I don't want to spend too much time because we will talk more about that. But we can quickly, for example, skim through. We can look. I want to look at the power loss, for example, the power loss curves. Yes, sir.
What I meant was, so we got our PWM signal now,
Yes.
and we can apply Fourier series or Fourier transform,
Yes.
and we try to filter the lower frequencies with the LC filter.
Sure. Okay. The low pass filter.
This is what we're doing, right?
That's what we did. Yeah. That's what we were doing.
Okay.
So we have this pulsed waveform, which is an AC waveform plus a DC waveform. It has an average value. What you would like is to get the average value out, which is the 3 volts. So how would you do that? It's a waveform with a lot of frequency content, including DC. You only want the DC out, so what do? You will low pass filter. If you let's look at the Fourier series for this waveform, okay? If you look at the Fourier series, I have the Fourier series data sheet, Fourier series equation sheet here for you. Fourier series waveform, common waveform, okay? So let's look at the Fourier series for, fine, this is not exactly the same waveform because this has an average value of 0. This is, I don't know if I have a, yeah, this has, yeah. What's the difference between this waveform, these 4 waveforms, and the bottom 2?
AC and DC.
What do you mean AC and DC?
The 4 on top are AC.
Yeah, the top 4 waveforms have areas on top and areas on the bottom that are equal, right? This area is equal to this area equal to this area equal to this area, which means if the areas on top of the 0 axis and below the 0 axis are equal to each other, then this waveform has 0 average value, right? It's an AC waveform. It only has AC components. So if you look at the Fourier series, even the first component, there is no average. Fourier series is A0 plus AN sines plus BN cosines, right? That's one form of the Fourier series, if you remember. So it's average value plus sinusoidal components. So these 4 here, as was said now, don't have any average values. But if you look at these waveforms don't have an area under the curve anymore. So obviously these waveforms have an average value. So our waveform is similar to these. Right? It would have an average value, and then a set of AC values, sines or cosines. I don't care, right? But it has an average value and a set of sines and cosines. If you look here, what is the first frequency after DC? This is Vm over pi is a DC average value. You agree with that? This is the DC average value. It's a DC component. How about everything else? Everything else is an AC component. What is the first component after the DC? At which frequency? At the frequency 2 pi, at omega, right? This omega is the same frequency as the original waveform that was placed inside. So now I have a big, I have something DC, and I have something at 50 hertz, or at my switching frequency. Because in this case I have omega will be my switching frequency, right? So I have something at DC and something so high up there. So it's easy to separate them. If I put a low pass filter anywhere above DC, fine, I'm happy, because I'm switching typically, in the hundreds of kilohertz or tens of kilohertz, etc., and then I have something at 0. Right? So I put a low pass filter. It's easy. I will easily take out the average value from the original waveform. So that's exactly what we did. We put a low pass filter. So we had a pulse waveform here. We wanted a pure DC, so we had to add a low pass filter. After you add a low pass filter, now what is the efficiency? Here, the efficiency was almost 100%. I have an ideal switch, right? Switches on, switches off. Switches on, it has, if we're operating, if I'm assuming that I'm operating the MOSFET in this fashion, this is V, this is I. If I'm operating along here, these are my two operating points. This is voltage of what? 0, and current I. And this is current of 0, right? And voltage V. So this is some voltage V here. This is my voltage axis, and this is my current axis. This is current I, this is voltage V. So I'm operating here with 0 power loss, and here with 0 power loss. But I'm actually, and this is ideal, I'm not really doing that. I mean, this is in reality, what's actually happening, this line is actually to the little bit to the right. This is the reality. This is the characteristic curves of the MOSFETs or BJTs or whatever device we will talk about today. Right? These are the curves. I don't care about this side, this part of the curves. I will not use it that way. I will only use it along this straight line and this line. Which means, fine, I have some power loss. If I want to operate at this current, I actually have the same current I, but I have some VDS here. I have some VDS and some current. If I'm talking about the MOSFET, this is my drain to source. This is my plus minus drain to source voltage. I do have a voltage drop because of the channel resistance. And the value of the channel resistance is inverse of this slope. This is a linear line. V equals IR. This is V that I have. I plug it here. And this is the I that I have. I can plug it here. I can calculate R, the corresponding R. Is R going to change? No, because it's a straight line. R will always be the same. It's a straight line. Right? There is a linear relationship between them. Yeah. Okay? So, ideally, I would like to increase switching frequency. I cannot because of switching losses. That's one thing. And I cannot because of the limitation on rise times and fall times that we have in the switches. We saw those in the datasheet. There were rise times and fall times that we have in the datasheet. They limit your ability to actually produce a proper turn-on time. We call it duty cycle. So the amount of time the device is on is, you can call it the turn-on time or the duty cycle. It's called, in power electronics terms, it's called duty cycle, the turn-on duty cycle. The amount of time that the device is on. If I'm going to choose a device that's slow, I'm thinking I'm getting a certain amount of turn-on time while I'm not. What is that going to do? It's going to affect my average value. And what am I doing in power electronics? All I'm doing in power electronics is I'm taking these waveforms, chopping them up, and then producing an average waveform out of that. So if I'm producing an average waveform that's wrong, then I'm not doing my job. Right? That's the whole objective of what we're trying to do here. Okay, so they're all tied together. So you increase switching frequency, then if you increase switching frequency, I can use smaller capacitors and inductors. But if I use increased switching frequency, I have to choose the proper devices, and I have losses. I will be converting the losses from, it's a compromise between the losses in the devices, the losses in the capacitor, the losses size of the capacitor, etc., etc. Right? So we went here from something that has ideally 100%, and I think, do we all see why I say the switch will have ideally 100%? It's because I was operating on these curves, these two curves here. If I'm operating on the real curve, then the switch will have some resistance when it's on, right? But this value of resistance, is it big? If it's big, then the voltage will be big, right? Because fine, I have it for a certain value of current. If it's small, then the voltage will be small, and what I have is really, it's the voltage will be small. I'm operating on a very narrow part of the device's characteristics here, right? So it's a small value, and if you go to the datasheet, for example, for this device, they will have it, we said it's what? 8 milliohm for this device. So depending on the device, you will have a certain value of this resistance here. Anyway, so we're basically operating with nearly 100%, if 8 milliohms. 8 milliohms times 100 amps, so 8 watts. Right? Versus if you were dropping here across this 6 volts times 100 amps, that's 600 watts. 8 versus 600 watts. Can you see the magnitude difference? Very, very large difference. So that's why in power electronics, it's almost, we talk about ideal switches a lot. The device is an ideal switch. And because it's, compared to what it would have been for a linear regulator, it's a lot less loss. So it's almost 100% efficiency. But now, if we add this filtering stage, there's losses in the filter. Capacitors, the capacitor is not an ideal device. An inductor is not an ideal device. The capacitor is, or the inductor is what? The inductor is a set of wires. The set of wires has a resistance. It's a copper wire. Has a resistance. So you're typically modeling inductors as an ideal inductor with a resistor in series. A capacitor is, you have an inlet into a capacitor, then you have a plate that's a conducting material, metal plate that's a conducting material, and then you have a dielectric, and then you have another conducting material. Right? If current is flowing, then there is current flowing through a conducting material. So we also model capacitors as an equivalent series resistor. We call it ESR. So it's called equivalent series resistor. And this is the equivalent series resistor as well. So these are equivalent series resistors. So we model it as an equivalent series resistor and an ideal device, ideal capacitor. Ideal capacitor has no losses. Ideal inductor has no losses. Right? There's no loss. There's no real power loss in an ideal capacitor. There's no real power loss in an ideal inductor. But real power capacitors and inductors, they're modeled with resistors in series. So now, after you add this filter, you get a hit on the efficiency. So it's no longer 100%, it's lower than 100%. How much lower? Depends on the type of capacitor and type of inductor you choose. Okay, how do you choose an inductor with lower resistance? What affects the resistance of a wire? Resistance is equal to rho L over A, right? So the resistance is inversely proportional to the cross-sectional area of the wire. So, which means that, fine, I can choose a very big wire. If I choose a very big wire, I have a low resistance for the inductor, which is great, that's fine. But big diameter, you still need a certain number of turns to design an inductor. We will talk about that a little bit down the road, but bigger wire means you have bigger size. Bigger size means more copper. More copper means more expensive. So it's heavier, it's more expensive, but it's much more efficient. Right? So it's a compromise. Same with capacitors. You have capacitor technologies that you have electrolytic capacitors, and then on one end of the spectrum, and then you have ceramic capacitors on another end of the spectrum. Right? These capacitors are very expensive, but they have very low ESR, very low ESR. So ESR is very low, but they're very expensive. So if you want to buy 1,000 microfarads from this, you will pay 100 times more than 1,000 microfarads for that. Right? But this electrolytic capacitors, their ESR is high. So ESR high, cheap. You can easily buy them. You can buy in large sizes, etc., etc. This very expensive. And in the middle, you have many kinds of capacitors. You have, and I put 2 videos on the various types of capacitors. It's nice to watch. There are 2 videos here on capacitors. I would recommend you watch them. They talk about the different types of capacitors, the differences in cost, differences in performance. It's good common knowledge here. Okay, so these are what we have there. So anyway, so that's what we have inside this filter. So this filter will affect power loss. So you will design this filter with different capacitor and inductor technology. This will affect power loss, and you will get a hit based on the quality of capacitor, the quality of inductor that you have. But you're not limited only by the quality that you have. You're limited by the application. If you want something to put in a mobile phone, obviously you cannot pick a big wire. You have to live with a small wire, which means you will have high resistance. So what do you do in that case? You try to reduce the current and maybe increase the voltage in that case as a compromise, because the power loss is I squared R in that resistor. So, but if I increase the voltage and decrease the current, I can live with, be able to transfer the same amount of power with better power, with a better efficiency, if you want to call it that. But then you cannot increase the voltage too high, because this is a device you're holding in your hand, right? You cannot hold a device in your hand that has 1,000 volts, for example, inside it. Right? So there are many considerations. So at the end of the day, there are safety issues, performance issues, size issues, cost issues, and that's what you do in power electronics. You compromise between all of those to come up with a converter. But the topology is very similar. All the topologies for the power converters are very similar. And again, we talked about changes in the load. You want to do all of that. You want to make sure that you're regulating the voltage in the presence of changes in load. And you want to do that also in the presence of changes in the source. Right? We said that this 240 volts is not fixed 240 volts, or AC value, fine, but its RMS value is not fixed at 240 volts. It fluctuates within a certain range. Are you going to accept? Is your load going to accept that? Maybe yes, maybe no. If your load is not going to accept that, then you have to make sure you're controlling your power converter so that the output is always fixed, regardless of input changes. Right? Or if your output is changing, you want to make sure that the voltage across the output is always fixed, regardless of the load changes. Right? So that's something else we will be discussing. And the way you do all of that is, of course, you build the converter. So how do you build the converter? Converter is switches, reactive elements, and control. Switches, reactive elements, and control. That's it. Switches, reactive elements, and control. So there are many types of switches. The simplest are the diodes, and there are we go to many different. We'll talk about a few ones that are interesting. And we will operate all of these devices in this cutoff and cutoff mode or saturation or triode, depending on the type of device technology. All of them will be operated the same way. Right? So we will talk about a few devices that are important. Diode, of course, you've studied in 325. It's one of the most commonly used devices in power electronics. I think in 325 you studied some rectifier circuits as well. Right? You went through some simple rectifier circuits, full bridge rectifier, half wave rectifier. We did that in 325. We will review that here, but here we will spend more time to analyze the circuits, draw waveforms a little bit more, spend more time doing stuff like that. So again, the diode is the first device that we will talk about. It's called an uncontrolled device. Uncontrolled meaning I'm not the one that dictates when to turn it on and when to turn it off. When you put it in a circuit, the circuit dictates when the device turns on and when the device turns off. Right? When does a diode turn on, for example, in a circuit like this? And this is an AC waveform like this. Yeah, it's a sinusoidal voltage at the input. So what does the output voltage look like? The top part, the first half cycle, right? This is called the first half cycle, second half cycle, right? So I only get the first half cycle at output. Why is that? Because the device will turn on when the voltage here is more positive than the voltage here. Or if the circuit, so who's doing this voltage polarity thing? The circuit is doing it. It's not the diode. The circuit is forcing the polarity of the voltage across the diode to be in a certain fashion. So this is an uncontrolled device. It does whatever the circuit asks it to do. If this circuit somehow is forcing current to flow in this direction, somehow, We don't know what the circuit looks like. It's a circuit that forces current to flow in this direction. The device will turn on as well, right? So, but if the circuit is going to try to force current in the opposite direction, what will the diode do? Block, right? And that's what happens in the second half cycle. So in the second half cycle, you remember, voltage and current across the capacitor are in phase, right? If you put a sinusoidal voltage, you will get a sinusoidal current. Exactly the same shape, in phase, but shifted in magnitude, correct? So what was the circuit trying to do? The circuit was trying to, initially it was putting a positive voltage. Positive voltage on a resistor means positive current. Positive voltage, positive current, right? This is what, V equals IR. Positive voltage, positive current. But now if I put negative voltage, it's the same resistance, it means I have negative current, right? So when the circuit tried to put some negative current, the diode blocked it, right? So that's what, the circuit tried to do something, and the diode behaves based on what the circuit tries to do. If it tries to force current in the opposite direction, it will block, and that's what happens, and it stopped, right? Between this transition between, this diode is nothing but what? Remember, if you're 325, it's a PN junction, right? When the diode, you remember when the PN junction was not connected to any voltage at all, you had what is called the barrier voltage. We created the depletion layer, and there was some barrier, diffusion current and drift current and all of that kind of stuff. Again, we don't have to review it, but there was some barrier voltage developed, right? This barrier voltage was the one that was stopping the diffusion current from flowing, right? So you had this barrier voltage that was stopping the diffusion current from flowing, meaning the charge is moving from P side to the N side, and vice versa. They were stopped by this barrier voltage. When the device was forward biased, the depletion layer became very small, and you were easily allowing to push the charge, the diffusion current to flow, and the device was conducting. When the device was reverse biased, the depletion layer was becoming very thick, right? And the barrier voltage was increasing. So the barrier to the diffusion current was increasing in that case, right? So what was happening, the depletion layer was being filled with these charges, the positive charges on one side, negative charges on one side, to create this barrier voltage, this larger barrier voltage, to put the device in reverse mode, or shrink the depletion layer so that the charge, the drift current the diffusion current can go through, and the device would conduct. This required some time, right? So there is a transition between the on and off that we don't show here very much. There's a transition between on and off where you are gonna fill the depletion layer with charge, or remove the depletion layer, remove some charge from the depletion layer for the device to conduct, right? And that's what we have in this performance curve here. So the device was conducting, meaning the depletion layer was very small. Now I need to put charges to increase the barrier voltage so that the device can block. That is called the reverse recovery time. So you had the device on, it went to off. Between this on and off, there's a period where you have to charge the depletion layer again so that the device stops conducting. The barrier voltage becomes big again. And this involves putting charges in an opposite, putting charges using opposite polarity of current than your conducting current. Yes, sir.
So that happens naturally, or is
Yeah, naturally. No, it happens naturally because if you remember your 325, you had they had three pictures. They had when the PN junction had no voltage across it. PN junction with a voltage polarity in one direction so that the device is forward biased, and then one where the voltage polarity is such that the device is reverse biased, and they had the depletion layer thick on one side, thin, and then average value where the barrier voltage was 0.7 volts, right? So just how do you, there's time required, and movement of charge means current. So this is this current that is required to build up the larger depletion layer, right? So the device was on, now became off. This reverse recovery time is the amount of charge required to build the depletion layer again.
That's assuming there is a negative, backward
negative voltage on.
Assuming you apply minus VD on the diode.
Not minus VD. No. Of course. When does the device turn off? The device turns off. So we said here. So this is the characteristics of the current, performance of the diode. This is the polarity of VD, and this is the the direction of ID. If VD is positive, what happens to the device? It becomes on, turns on. And remember the exponential curve for it to turn on? This is this exponential that we studied in 325, right? And when the VD polarity is negative, the device is off. Up to some point, you're going to reach a breakdown voltage. And you will, like the Zener breakdown operation, but, this is non-reversible in this case for classical diodes, not a Zener diode. You put enough negative voltage so that you basically are burning the diode. You're pushing this diode to an irreversible failure. Yeah. So this is the full performance curve of the diode. This is a dynamic effect that's not actually shown here. And this reverse recovery time is a dynamic effect that is not. This is a curve without the respect of time. This has no respect of time. Right. So you went from a device on to a device off. There was some reverse recovery current, and this is something that's in the datasheet of the diodes. I don't know if I have a datasheet of a diode. I do have. One second. This is the reverse recovery current. It's the value of the current. So it will have a corresponding current. This is a current, right? This is a current, a value of current. This is not equal to the load current. This is the current required to fill the depletion layer with charge. So it's a physical characteristic of the device. So it's always going to be a fixed value like for a certain device. So this is reverse current. It's called the reverse recovery current. Let me see if I have the reverse recovery time. Should be here somewhere. No? 11, the characteristic. Reverse current. Unless this is a Schottky diode. 1 second. Not a good data sheet for a diode. But I'm sure this MOSFET internally has a body diode. I'm sure they will have the reverse recovery time for that. 1 second. So this is the source to drain characteristics. The source to drain characteristics mean the characteristics of this diode. See, it will have a reverse recovery time of 100 nanoseconds in this case. So it took 100 remember, it took 100, it will take 100 nanoseconds to bring it back to recovery, to block again, yeah. And then you have to remove a certain amount of charge, or fill the depletion layer with a certain amount of charge. About 150 to 200 nanocoulombs for this device, right? So this is what is required to bring it back to blocking, or remove allow it to become forward biased. Okay. But it's not something you can see on the characteristics. The IV characteristics. It's a dynamic effect that you see in a circuit. Okay. Yes, sir.
Yeah. Does the backward voltage affect the recovery time?
Backward voltage affect the recovery time. So
if I apply backward voltage
No.
on the diode to turn it off right there in the middle of the analysis, does that shorten the recovery time?
A certain amount of backward voltage? I don't believe it does, because there is a certain amount of charge that needs to be removed, and this reverse recovery time is a fixed amount of time. I think it's for a specific value of current. Yeah, so it will, for a certain value of current, obviously. Because charges, they give you the charge, right? If you have a high voltage that will be pushing in a high current, then you will be able to push this charge quicker. But it still has this reverse recovery time has still typical values and maximum. They will give you, so typical value is about 70 nanoseconds to 100 nanoseconds. So if it's a higher current that's doing it, maybe you'll do 100 nanoseconds. It's in this range, right? So, but yes, I agree. It's given at a specific value of current, because charge is time variation of So current is the time variation of charge. So yes, if you have a higher current, you can do this faster. Yeah. But it's the physical phenomena that's of interest. Yeah. Why is it of interest? Typically because of this. We will see in power electronics a lot of times that we will have circuits that maybe will have something that will look like this, or yeah, something like that. If they will look like that, circuits that will look like this, for example, we typically operate it such that the top device is like, let's say this is my battery. I would typically do this. I would turn on the top switch, for example. If I do that, I'm connecting the battery's positive to my load. Let's say this is my load. Okay, so I'm connecting the battery's positive terminal to my load in this case. How about if I turn off this device? If I turn off this device, if this current is inductive, remember, inductive current does not change abruptly, right? If you have an inductor here, remember in 214 you had you talked about IL of 0, initial conditions, and then this will dissipate with time if I have a resistor in the circuit, right? I have some lossy element in the circuit, yeah. So if that's the case, if I have an inductive type current, what's going to happen as soon as I open this switch? As soon as I open this switch, the current will start to flow in this loop through the diode. Just keep flowing here until the energy that's in the inductor will dissipate in the resistor. That's how this circuit will operate if I don't do anything else, right? I can do something else then. I can go back and excite it again. Turn on this switch. If I turn on this switch, I will reverse bias this diode. Because if I turn on this switch, I'm putting this positive voltage V here. This is my positive voltage V, and this will be my ground. So I'm putting a voltage here that's more positive than here, that I will reverse bias this device. This will be an open circuit. And then, again, I'm putting a certain voltage across my load. And then I can open it up again. If I do that, then this V does not exist. This V that I put here does not exist anymore. And what is the circuit? What is the condition that is forcing the diode to be on? It's the current, the inductive current that's flowing through here. It's a circuit that is forcing a current in a certain direction. So the diode will turn on and conduct again, right? If that's the case, what was happening? We said that we talked about reverse recovery. The diode's on, and then before it goes off, there's some time when there's a reverse recovery, when there's current still flowing through it. If current's still flowing through, that means it's like a short circuit. Okay, so now let's consider this case. The diode is on, and I want to turn it off by turning on this MOSFET. Okay, if the diode is on, and this is diode current, diode is on, and I want to go to off state. I will go to a state. I have a transition state here, where the device is trying to recover. But what is the MOSFET doing at the same time? MOSFET was off, and then MOSFET tried to turn on, right? They're opposite of each other, right? MOSFET, this is MOSFET, diode. MOSFET was off, and then I turned it on. If I turn the MOSFET on, we said what's going to happen. Ideally, if I turn this MOSFET on, it becomes like a short circuit. I put this V here. If I put a V here, then I turn off the diode because I'm reverse biased, right? So, but in reality, this is not happening instantaneously. Instantaneously, actually, as soon as I turn on the MOSFET, the diode, okay, I need to start blocking. How do I start blocking? For me to start blocking, I have to do what? Current is flowing in this direction, right? But what's going to happen as soon as I turn on the MOSFET? So as soon as I turn on the MOSFET, current will flow from the battery here, and then it will do what? Is this diode blocking? Not yet. So what is it going to do? It's going to force current in the opposite direction in this diode, right? Current was flowing this way in the diode, right? It was flowing this way in the diode. But in a dynamic state, dynamically, and during a very short transit amount of time, because the diode is not blocking yet, what happened is I turned on the MOSFET, and this reverse current coming from turning on the MOSFET is now being split up between trying to put the diode in reverse mode so that it starts to block, and of course feeding the load because it's a parallel impedance. I have a path here and a path here. Current has two paths. It will be divided up based on the impedance of the path or how much blocking reverse voltage is blocking the current, etc., etc. But at the end of the day, this is this current that's going to flow here for a while. This is not going to flow there forever. It cannot flow there forever because the diode should not allow current to flow this way. But only instantaneously, very dynamic during this transitional state, it will allow that, so that it starts blocking again. So basically, it builds the depletion layer, and then builds the barrier voltage to be high, so that it blocks again. Okay, so this is how a diode would operate typically in a power electronic circuit. Okay, and that's why. So then, but the most, as a power electronics person, you will not really be okay. Fine, this is. You have stages of development. You first develop your topology. And then you typically develop your control. And then you sort of worry about details after that. So you worry about, looking at details of power loss and stuff like that. Will come after that. That's part of the design stage. So you first sketch up your circuit. Okay, this is the circuit I will use. This is how I will control it. The control stage, I don't really care about power losses yet. Because control stage is important. I want a range of voltage between so and so. I want a range of current between so and so. I can consider my switches as ideal during this time. And that's what we do a lot of the time. So in power electronics, a lot of the time we consider the switches as ideal during the initial stages of the design. And then we get into, of course, we cannot consider an ideal forever. We then have to consider the power losses. So that's why we will draw IV characteristic that looks like this. So instead of this exponential that has some voltage drop when there's current, meaning there's power loss, forget about that. I don't care. When the voltage is positive, the device is conducting. So here, when I put a positive VD, the device will conduct. When the voltage is negative, the device is off. So ideally, the diode behaves in this fashion. So this is the ideal IV characteristic of the diode. This is the real IV characteristic of the diode. So initially we'll utilize this, and then we will get into details and utilize this when we are going to come to what? Pick the device. First we pick the topology. Do I care how much power loss is in this device? No, not yet. I will put an L, I put a C, I put a switch, I put a diode, but I didn't pick it yet. I just put it there. Then I have to go and pick it. For me to pick it from the data sheet, then I will have to utilize the real IV characteristics. Okay, so that's the development stage here. Again, we have what is called a Schottky diode. That is a special kind of diode that has a very small amount of reverse recovery charge. So silicon carbide diodes are an example of a Schottky diode. So this, in a silicon carbide diode, or a Schottky diode, silicon carbide Schottky diode, this amount of reverse recovery charge required to build the depletion layer for it to block is a very small amount. Very small amount. Which is why there's a lot of buzz about silicon carbide. Right? Because then you don't have this current flowing in a circuit is lost. And because this is not useful for anything. This is not powering up your load. Remember what was this doing? This was just flowing in the opposite direction so that my diode can start blocking. It was something to functional. It's not something that is feeding my load. So if it's not feeding my load, then it's not useful. It's losses. Right? So the reverse recovery charge is not something we want. We would like to live without it. But of course, diodes with very low reverse recovery charge are expensive. Diodes with high reverse recovery charge are cheap. Right? So cheap and not efficient, expensive, efficient. You choose based on your requirement. Yeah. Anyway, so diodes are something you studied before. Thyristors are nothing but evolution of the diode. We did not study that in 325, but think of it as a diode. It's drawn as a diode, but with a control input. It's a gate signal. It's called a gate signal, and this gate signal is only a control signal to allow you to turn on the device. As soon as you turn it on, it will think it's a diode. So how will you turn off this device? No, you do not turn it off. You do not do it. You cannot control turn it off. It will behave like a diode. As soon as you give it a gate signal, it turns on. It will say I'm a diode. How does a diode turn off? The diode will turn off if it's pushing reverse. If the circuit is going to be pushing reverse current, or it's going to be pushing reverse voltage. If VAK is going to be a negative. it's this or that, right? If current goes to zero, as soon as current goes to zero and tries to become negative, the device will turn off. Right? So this is a device, and that's why it's called a semi-controlled device, because it's, you know, the diodes are called uncontrolled devices. These thyristors are actually the workhorse of the power electronics industry. These are the, you know, most commonly used type of device in a lot of applications. Yeah. So, and because they're very simple, it's a diode, it's a PN junction. It's actually nothing but a PN junction with a way to activate, to turn on the PN junction, meaning to control the depletion layer. That this gate is used to turn it on and turn on the device, right? So what does this look like? So if VAK is positive and I don't have a gate signal, the device is off. If VAK is negative, the device is also off, like a diode. But if VAK is positive and I give it a gate signal, the device will turn on. I will have current flowing through it, like a diode. Right? If you look at the diode IV curves, it's this, it's here. The only thing I added to this was, so I still have the diode IV curves, but I have this here indicating that fine. Even though I have VAK being positive, which is a condition that would have turned on the diode, but I didn't give it a gate signal. If I don't give it a gate signal, this thing does not turn on. As soon as I turn it on, it behaves like a diode. So if I, you know, draw a simple circuit here. I have a voltage source, a resistor, I have a thyristor here, right? Vs, and this is plus minus VAK, and this is the gate current, right? So, and this is a device that is, as soon as you turn it on, as I said, as soon as you turn it on, it will act like a diode. You do not need to maintain the gate current on there. So if this is IG, gate current, I will give a pulse, let's say here. And if I give a pulse here, what does the output voltage look like? And what does the output current look like? What does VAK look like in this case? I out. Until I get the gate pulse. What is VAK? 0. After I get the gate pulse, huh? What? What's the problem? What? Come again, sorry. So let's do current first. Sorry, let's do current. If initially I have if I have this circuit, okay, and I provide the gate signal here, what was happening to the current before the gate signal? It was 0, right? And then how about afterwards? Huh? It becomes Vs over R. Right? Because this device becomes a short circuit. And then what happens to the corresponding voltage? Initially, the voltage VAK.
It's supposed to drop.
Hmm?
VAK is supposed to drop, not rise, right?
VAK is going to drop, yes. Initially, it's blocking the voltage. Initially, okay, this is an open circuit. Right? This is an open circuit. If it's an open circuit, let me measure the voltage across the open circuit. What does if you remove this device, it's an open circuit now. What is the voltage across the terminals of the device? Huh? There's no current, so the voltage will be Vs. And then when the gate signal arrives, the voltage will become 0 or 0.7 volts, because this is like a diode, right? It will have the barrier voltage across. So I'll draw it to be 0 because ideal. So it's like I will operate like on the ideal IV characteristic, so it's 0. So this is what this circuit will do. How about if I flip the device? If I flip the device and I do this. and I provide the gate signal at the same time. So what's going to happen to the current and the voltage? Current, I output will look like what? It will never conduct, right? Because I will never be putting this voltage needs to be more positive than this. It's never going to be satisfied. So the current will be zero, the voltage will be zero all the time. The voltage will be what? Vs. The voltage will be Vs all the time because it's always an open circuit, and the current will always be zero in that case. So this is a thyristor, and these thyristors are very nice because of here I'm not showing the device being turned off because right here is the device ever going to turn off? Halas, here it's always going to turn on. It's always going to stay on. But in AC circuits, the voltages and currents always cross zero, right? So these devices are very commonly used in AC circuits. And they will be the workhorse of what you will use in the AC voltage controllers, for example. Anytime, and then they will turn off anytime the current tries to go below zero. Current tries to go below zero, it will turn off. Then the voltage is gonna, the voltage VAK is positive, but I don't get my gate signal. What does that mean? It means I'm not turning on even though the diode would have turned on, which means I'm able to control my turn on time. Yes, sir. Leakage, again, there's of course leakage. All devices, if you put a voltage across them, even though they're off, they will have leakage current. Yeah. And this will be something, I'm sure in the datasheet, let's say for this device, I'm sure you will have some internal drain, blah, blah, blah. Leakage current. Any device will have, drain to source leakage current. 25 microamps to 250 microamps, depending on it. You see what's happening at temperature? So the conditions are very similar. The VDS is the same, voltage is the same, the gate voltage is the same. But when you increase the temperature of this device, for example, the leakage current increases a lot. Right? So any device will have leakage current. How much will depend on the device itself. Yeah. That's why it's very difficult to build devices, converters for high temperature. Yeah. Anyway, so this is the thyristor. We will spend a lot of time building circuits with thyristor. Any questions on the thyristor? And then, of course, thyristor, what was the disadvantage? That I cannot turn it off. That was one disadvantage. The other disadvantage that I didn't talk about is that this gate, I talked about briefly, I said that here is the gate current, right? Gate current is okay, but if I'm able to, typically thyristors require a high gate current to turn on. That's one disadvantage of a thyristor. If you remember MOSFETs, how does a MOSFET operate versus a BJT device? How do you turn on a MOSFET? Yeah, with the gate to source voltage, right? How do you turn on a BJT? Yeah, with a base current, right? And the base current has to be continuous, right? But MOSFETs, you provide a gate voltage. And what is the device made of? You had the gate, then you had an insulating material, and then you had the channel. Remember, this looked like a capacitor when you took 325? Capacitors, as soon as you place a voltage across them, they will draw some current to charge the capacitor and bring it to a certain value of voltage. And then what happens? That's it. You have a voltage source with a capacitor across it. As soon as the capacitor is the same value of voltage as the voltage source, then no current will flow anymore, right? Which is one of the big advantages of a MOSFET versus a BJT type device. This is current controlled, and you require current all the time to keep the device on. MOSFETs, they don't. So what people did was, they realized that thyristors are like BJTs, they're current control devices. So, which is fine, and I cannot turn them off. So the power electronics people came up with thyristors that you can turn off. And that's why, that's what you see here, like a bidirectional sort of thing, bidirectional arrows on the gate. So this is a thyristor that you can actually turn off. Then people came up with a different family of thyristors. I don't think I should show a picture here, that has a gate that looks like a MOSFET. So instead of being current control, it's voltage control. So it was called the MCT type device. So then, we will not be involved with, we will mainly be looking at circuits with thyristors, the basic thyristors. But what I would like to show you is, like we will talk about MOSFETs and BJTs shortly, people also, worked on the diode. Then they came up with a thyristor. Then they came up with thyristors that you can turn off. So it's called the gate turn off thyristors, the GTO. And then they came up with MOS controlled thyristors. So it's a thyristor that you can turn on and you can turn off, but the control signal is a voltage instead of a current, right? Because then it's easier to turn it on and turn it off. So all of them behave, similarly, but they're names that you need to know. But we will mainly be concentrating on the basic thyristor. Another name for the thyristor is SCR. Same thing. It's called silicon controlled rectifier or thyristor. Exactly the same. And then when you have two of them, sometimes we put two of these thyristors in a package, and they provide them with the same gate signal. If you do that, it's called a triac. Just another name for it, but it's basically two thyristors back to back, but with the same gate signal. When is this used? It will be used in chapter 5. We will look at how to use it. Yeah. Okay, transistors are the last. So we had uncontrolled devices, then we had the semi-controlled devices, then thyristor and the MOSFETs or BJTs are the fully controlled devices, because these are devices that you can fully turn on, controllably turn them on and turn them off anytime you want, as long as you satisfy the conditions. MOSFETs and BJTs, in 325 we had certain DC operating point conditions, right? If you satisfy those, then you can turn on the device and turn it off anytime you want, right? So that's why these are called fully controlled devices. Yeah. So, and again, one is voltage controlled, which is the MOSFET. One is current controlled. The disadvantage of current control, as we said, you have to maintain the current all the time. So people in power electronics don't really use BJTs at all. They came up with a hybrid that they called IGBT, and I'll talk about that next. So anyway, the MOSFET, we talked a lot about that. You studied in 325. As we said, we only operate in the triode and cutoff, right? So, and this is the ideal voltage current characteristic. Yes, sir.
About the MOSFET, why did they draw the
This?
thing to the left?
That thing to this?
Yeah.
Well, it's one way to draw. I mean, there are many ways to draw symbols of a MOSFET. Actually, it's a good point that you brought this up. I will draw in this course. Let's just agree that the way I will draw a device is this way. I don't care. We will not care later if it's a BJT, MOSFET, or whatever, because for us it's a switch, right? Fine. If I tell you it's a BJT or tell you it's a MOSFET, then maybe it will change the way you calculate losses. But I will draw them all the same way. I will draw them such that this is the direction of current flow. So the arrow will point to the way that current is flowing. Fine. MOSFETs are drawn in a different way. BJT is drawn in a different way. But I will typically just utilize this symbol for a switch in our case. So this is an NPN MOSFET, and they draw this diode because of, if you remember the structure of the MOSFET, it's a PN. For example, if it's an N-channel MOSFET, you had a P substrate and then two N-channels, two N-channel materials on top. So it was a device that is 100% sort of symmetrical, but the P and N, between the P substrate and the N source, between the P and N junctions here, you have a P here, an N here, another P, N the other side. So let's say here. So you have a device that looks like this, right? N P. This is a PN junction, so it's a diode. This is a PN junction, so it's a diode. Right? So these are diodes. And we typically connect, so this is what? Gate, and this is drain, and this is source, and this is called body. And we were typically connecting, remember, we were typically connecting the source to the body, right? And that's what we have. And here, if you do that, you end up with a diode that is able to conduct if you, for example, are going to push current in the opposite direction, from source to drain. If you push current, it's called a body diode. I don't know if you covered that in 325 or not. But by construction, a MOSFET has this diode. Okay, so what does this do? It will destroy our characteristics. So we typically have ways to deal with it in power electronics. Yeah. So for now, the device will conduct current only in one direction. So what does this device do? If VDS is in this polarity, this device will block positive voltage, right? If VDS is positive, is current going to flow? If I don't have a gate signal. If I don't have a gate signal and I have VDS positive, what happens? I'm able to block the voltage. Right? If VDS is positive, I have VDS here, VD greater than VS. Right? It's a positive VDS. If VDS is positive and I don't have a gate to source voltage, I don't have a gate signal, then this device will block positive voltage. Right? If I put negative voltage, what happens across this device? If I put a negative voltage, this diode will conduct. I'm bypassing this device completely, which is uncontrolled. So we don't operate it in this mode. Right? That's why I don't include it here. I don't operate it in this mode. I want to be able to control something fully. I want to be able to, I want to have a voltage and be able to block it or allow it to conduct. Block it or allow it to conduct at my will. Right? So if I put a negative VDS, it's useless across this device. Then it just becomes a diode. Right? So, yes, sir.
Is the diode positive also?
Yeah. With the MOSFET, it's part of the structure of the MOSFET. It's internal. It's called the parasitic diode. If you go back to 325 material, you'll find the one section about the parasitic diode. I don't know if Dr. Bina covered it when you were teaching it. But it's there in the model, right? But I don't utilize, in power electronics, I don't utilize it that way because I cannot control anything that way. If I flip the voltage polarity, it's useless. So this device is beneficial for me if I'm able to block positive voltage, or if I give it a gate signal. If I put a gate signal, I can conduct positive current. Can I conduct negative current? No. Negative current will also be current that's flowing through the diode, so it's useless. It's uncontrolled. So this device is good for controlling positive current flow and for blocking positive voltage. Right? I'm able to block voltage, positive voltage, and I'm able to control when I allow positive current to flow. Right? When I switch it on, I'm allowing positive current to flow. When I switch it off, I stop allowing current to flow. So, and that's basically what we don't care about what's happening in this linear region at all. Okay, I just care about triode and cutoff, right? Same thing with the BJT. We will operate the BJT in the same way if we utilize it. For us, it's same. It will be a switch that will also operate either in the BJT. It's called saturation and then cutoff. So we will operate it exactly the same fashion. And for us, it's doing the same thing. It's blocking positive voltage. If VC is positive, and I don't provide a base current, the switch is off. It's open. So I'm able to block positive voltage. And then if I provide a gate signal, or base current in this case, I'm able to allow positive current to flow. Can I allow negative current to flow? No. This device will not allow negative current to flow at all. Right? So this is how I'm operating these devices as switches. The second level is to consider their losses by looking at the slope of this line. Right? The slope of this line will dictate at what value of current I have a certain voltage. We take the two, multiply them by each other. This will be the power loss in the device at that case. Okay? When the device is conducting, it's called conduction loss. When the device is switching, this voltage rising and current falling, or current falling and voltage rising, that's called switching losses. So we have two types of losses. We have conduction losses when the device is on, and then we have switching losses when the device is during this transient state when it's switching. Okay? But here it's ideal, right? 100%. I have zero current, full voltage. Zero voltage, full current. It's the ideal switch sort of approximation. We don't like this. Power electronics people don't like this because there's current being consumed all the time to keep the BJT on. So we typically don't use BJTs in power electronics. We utilize what is called an IGBT. So they brought the MOSFET and BJT together and built what is called an IGBT. We don't care about it. I'm not asking you to understand how the model works, but the concept is as follows. The concept is you have a MOSFET gate, but a BJT channel structure. So, a BJT looks like an NPN. It looks like an NPN sort of device. So you still have the NPN type of structure for the conduction of current. But the way that you're controlling the barrier voltages is through a gate, like the MOSFET, which is nice, because in this case I can provide a voltage, I don't need continuous current. Right? So this is the workhorse of a lot of the power electronics industry today. I will show you some. So just to sum up, we have uncontrolled diodes. semi-controlled, which is the SCR or thyristor, fully controlled, and this is how I will draw it. Typically, it's either MOSFET or IGBT or BJT. It's a switch. These are fully controlled devices, and this is how I will draw them. Current will flow in the same direction as the arrow, and positive voltage polarity is required for you to be able to control them. Yes, sir.
Does the IGBT block the reverse current?
Yes, it's exactly like these devices, like the MOSFET or BJT. It will block reverse current. It will not allow reverse current to flow, and it will block positive voltage and conduct positive current. It's exactly it's the IV characteristics exactly the same. But the only difference is the physics of operating the device, and which will affect the way you design your circuit. I don't have to provide continuous base current. I can provide a a gate voltage. In that case, it's actually called gate voltage, like the MOSFET. It's called, you provide a gate voltage between the gate and emitter. It's not between the gate and source like the MOSFET, between the gate and emitter, but it's exactly the same. You provide the gate voltage, and the device will turn on. The beauty is you don't have to have continuous current, which means less power loss. That's why. So we will get back to this slide later. This is a summary of the three types of devices that we will be discussing. I will get back to this later when we get into it. This is an application, that example that you have in a textbook. So you have a circuit where, again, as we said, we initially want to choose the topology. So how do you choose your topology? You have a circuit, and that needs to do something, and then you want to put some switches inside. Which switches, diodes or MOSFETs? You select based on the application. So let's look at here. Here we have a current source and we have a voltage source here. So we look at S1. Switch S1, what's happening? Current is flowing in the positive direction. And under this condition, the voltage across the device is 0, and I'm conducting full current. Right? So S1 under this condition looks like this. I have 0 volts, and I'm conducting current I0 here. Right? How about in the second operating mode of the circuit? I'm conducting 0 current, and the switch sees what voltage across it. If this other switch is closed, happens to be closed, this is the application. This is the application. You want to remove these switches and put a thyristor or a diode or a MOSFET. So what do you put in there? You look at, okay, now what is the voltage across this device? This device is short-circuited, so this is like connected to the bottom here, which means V1 is equal to Vs in this case, right? So under the second operating Vs or minus Vs? Vs. V1 is equal to Vs, yeah. So this is V2. So V1 is equal to Vs. This is one operating point. This is the other operating point, right? So this is one operating point for the switch. For second operating point for switch S1. For the switch S1, one operating point. Second operating point. I have 0 voltage and current flowing through it equal to the load current. Here I have Vs voltage across the device and 0 current flowing through it because it's open. So it falls on this type of IV characteristic. So what device satisfies this type of IV characteristic? You go back to your devices and, okay, you see that it's definitely not the diode, because the diode characteristic looks like this. So it's our required characteristic is something that looks like this, right? So it's either going to be a MOSFET or a BJT. It's a fully controlled device, one of the fully controlled. I don't care which one you choose in this case. It's one of the fully controlled devices. So that this is just an example that says, okay, if these are your 2 operating points, then you go back to your IV characteristics for the devices that we came up with. This is the IV characteristic of the fully controlled device. And that's why S1, I remove it, and I put a fully controlled device here. MOSFET or BJT, I don't care. And then same thing for switch S2. Here, I have 0 current flowing, and a voltage equal to minus Vs. Right? This polarity of V2 is equal to the minus Vs polarity. Right? So it's minus Vs and 0 current. And the other condition is conducting the load current and has a 0 volt across it because it's an ideal switch. So you go back, and this is probably the IV characteristic for the diode. So we were able to put a MOSFET and a diode here. This is a special case I will not discuss. There's no need to discuss that. But this is how you would select okay, this is the type of switch I need to put there. Then, okay, how do you, okay, buy this actual real switch? That's you calculate power losses, etc., etc. So I think that this ends the chapter. This other stuff we will talk about after we talk about other chapters. I wanted to show you this curve only, okay? And then we will end the class. So this is, as we said, there are many types of devices: MOSFETs, BJTs, IGBTs, thyristors, all over. So this tells you, for example, okay, this is the envelope of operating voltages and currents for different types of devices. So look at IGBTs. IGBTs can operate, up to 7,000 volts, maybe 900 amps, or up to 3,500 amps, but you have to go down to lower 1,700 volts almost, right? So this is the operating envelope for IGBTs. So once, fine. First, what we did in the example was, okay, we identified that I need a fully controlled switch. So I need a MOSFET, BJT, IGBT, whatever. I need something that I can turn on and turn off in a controlled fashion. Which device do you use? If you have an application that has voltage and current characteristics here, 4,000 volts and 3,000 amps, I cannot use an IGBT. So in that case, I have to go for something. I can either use a GTO or an SCR if the application is okay with applying the SCR, because the SCR looks like a diode in operating characteristics, right? But what this tells you is that, okay, MOSFETs, where would MOSFETs fall? MOSFETs are not shown here. MOSFETs would fall here. MOSFETs are here. You would not find the MOSFET more than maybe 1,700 volts, and you would not find the MOSFET more than a few hundred amps. So MOSFETs are down here, right? So they're good for applications like, washing machines, TVs, computer power supplies, etc., etc. Okay. Then if you have something that requires a fully controlled switch, that's higher voltage application, like a motor drive for a compressor, for example, or an electric vehicle or whatever, okay, you may need to go to something a little bit higher, like an IGBT. If you want to control a megawatt kind of drive with 12,000 volts and, 1,000 amps, you will not find anything but an SCR to do that. Right? So in that case, you have to choose a proper topology that allows you to utilize an SCR for that purpose. Okay, so that's the end of this introductory chapter. I think there are some PSpice simulations you will do in the lab to just do this. It will basically be a repetition of this example that I did quickly here, but using PSpice and drawing some waveforms and stuff like that. Any questions? No questions?